Welcome to Bio 1026, Chemistry of Life. Today we are in the lecture 7. We will talk about the Gross-Haldol and the Michael addition. Remember that this is a summary of the most important aspects of the lecture, but in the notes you will find a lot more things that I am explaining here. This is the basis. If you remember, in the last lesson we was talking about the aldol. Basically we have this compound, okay, and this can react with basic or acid media. We will do it first with base. The base will remove the hydrogen that is in the alpha position to the carbonyl group. We will generate the enolate. Okay, remember that you have two resonant forms, but I put always the resonant form with the negative charge on the carbon because it explains better the reactivity. And this is reacting with another molecule of the ketone. To form, after protonation, if we are doing in acid media, basically what is happening is that we form the enol. Remember, this is the first step, the formation of the enol. And this enol will react with a ketone that is protonated. Okay, remember that when we are in acid media, some of the ketone get protonated. We are increasing the electrophilia of this carbon. And simply what is happening is that we have the reaction. This is a nucleophile. We lost a proton, and what we get is the aldol product. Okay, these are the two basic mechanisms, the acid mechanism, the base mechanism, to generate the aldol product, to do the aldol reaction. Okay, this seems a very good method to do a carbon-carbon bond. However, it's quite limited because we are doing, basically, we are demedization of this starting material. The question is, we can use two different carbonyl compounds to do an aldol reaction? And the answer is yes. Okay, we can use two different compounds. And the typical example is when we are doing an aldol reaction with two different compounds, what we need to do, the first thing is to know who is the nucleophile and who is electrophile. Okay? Who is the nucleophile? In order to do the nucleophile, what we need to do is to find which of these compounds can form an enolate or a enol. Both options are valid. That means it's easy to find if they can form the enolate. Okay? Remember that in order to form an enolate, what we need is a hydrogen in the alpha position. Okay? Here, do we have any hydrogen in the alpha position? Here we don't have. And here is a hydrogen, doesn't have any more hydrogen. That means This hydrogen is directly attached to the carbonyl. Never remove this hydrogen. Never. Okay? That means the only possibility is to do the enolate in this position. Here is the same position than this. That means this is symmetrical. Okay? That means what we know is that this compound will be the nucleophile. And then we need to find which is the electrophile. And electrophiles basically are carbonyl compounds. I mean, this compound could be, this carbon could be, and this carbon could be. But what we know that by basic reactivity, that an aldehyde is always more active against electrophilic substitutions than not a ketone. Okay, aldehydes are more electrophile than ketones. Okay, and this is the key. We only can form the nucleophile with the ketone, with this ketone, and we know that between these two compounds, this will be more electrophile than the ketone. That means, first step, if we are in basic media, what we do is we form an ion, okay, with a base. We form the enolate, and then this enolate can attack himself, can attack another molecule of the ketone, or a molecule of the aldehyde. But we know that this molecule is more reactive. That means that will attack the aldehyde. And we follow exactly the same mechanism than before. What we get okay, and then when we attach it, what we get is the final compound. Okay? And from here, from the aldol, sorry, we can do the elimination that we explained in the last lesson. We can do the eliminations. If we are in basic media, we will follow a E1CB. If we are in acid media, we will follow a E1 procedure. What happens if we are in acid media? Well, what we will do is that we form the enol, and the important thing is that the enol can only be formed in the same position than the enolate. That means if these compounds cannot form an enolate, you will never form an enol. Please check it at home. Okay, we form the enol, and then we are attacking the protonated form of the carbonyl compound. Again, aldehyde is more electrophilic than not ketone. That means that this will attack the protonated form of the aldehyde. Okay, we have the protonated form of the ketone too, but these will be always, aldehydes will be always more electrophilic than not ketones. This attacks here. What we get is exactly than before. We lost the proton and we get the aldol product. Okay. That means this is very different that we explained earlier. No, it's exactly the same. The only that we need to do is that when we have two different compounds, we have to know which is the nucleophile and which is the electrophile. If you follow these two rules, first, try to find which of these compounds has hydrogens in the alpha position. That probably will be only one. And second option is check which is more electrophile. A more electrophile will be the one that is an aldehyde. Aldehydes are always more electrophiles than not ketones. And that's all. If you do these reactions, you will be able to do all the reactions with two different reactants. Then what more? Well, the second part of the lecture is related to the Michael addition. Michael addition or conjugate addition. You can tell it. You can name it as you wish. What is the Michael addition or conjugate addition? Well, what we know is that when we have a carbonyl group, okay, this is a carbonyl group, because the oxygen is more electronegative than not the carbon, what is happening is that we have a density positive charge in the carbon and a negative density charge on the oxygen. And we can represent this by a resonance form, okay, with a positive in the carbon and a negative charge on the oxygen. And this explains his reactivity. That means a nucleophile, a friend of positive charge, will attack the carbon because it's the one that has the positive charge. But what happens if instead of this compound, what we have is this one, this conjugated compound, with a double bond conjugated, okay? What is happening? Well, the basis is exactly the same. We have an oxygen that is more electronegative than the carbon, that means that will attract more the electrons. We have a density positive charge in the carbon, a density negative charge on the oxygen, same than with ketones. And we can do the resonance form, exactly than before. But now we can do another resonance form, isn't it? We can move this double bond here, and what we get this resonance form. That means if we can move the positive charge from the carbonyl position to the beta position, remember, alpha, beta, what we can say is that we have also this. Following the same analogy than before. We have a density positive charge in this carbon, in the beta carbon. Okay? That means if we join all together, what we have is that we have that in alpha beta unsaturated compounds, we have this density charge. We have a negative density charge on the oxygen, we have a density positive charge in this carbon, we have a density positive charge in this carbon. I will not enter in this carbon because we will not use it for the reactivity, but basically we have this position and this position that are electrophiles. Then when a nucleophile is coming to this type of molecules, what is happening? Well, what is happening is that basically can attack the beta position or can attack the carbonyl position. Okay? which will be more favorable depends on a lot of things. But you are lucky because in this course we will only study the reaction with nucleophiles in the beta position. We will not talk about the 1,2 position in unsaturated systems. In this type of compounds, we will only talk, the nucleophile only will attack the beta position. Okay? How is working? Well, we will put several examples. For example, we will start with this molecule. And we add a secondary amine. Okay? Well, what is happening is that the pair of electrons of the nitrogen can attack this position. Okay? We put the negative charge here. Don't forget to put any charge, please. Okay, and then the next step is we need to get a neutral compound. That means that when we do this, we can remove this hydrogen. Okay, we lose this hydrogen. And next one, we add a hydrogen and we get our final compound. Also, you can do exactly in one step. You can say that this negative is taking this hydrogen and we get the final compound. Okay? The pair of electrons of the amine is attacking the double bond and we generate this final compound. The question is, this reaction requires a slightly catalysis. Okay? We need a basic catalysis. Okay? I mean, we need to add some, for example, a base catalytic. Okay? This is happening with primary and secondary amines. But what happens if we are using a tertiary amine? Well, if we are using a tertiary amine, the first reaction will take place. That means this will attack the nucleophile, and what we will get is this intermediate. What's the problem now? Now the problem is that here, in order to make this nitrogen neutral, we cannot do anything. We cannot lose a proton. We cannot lose a proton because no hydrogens. If we cannot lose a proton, this becomes very unstable, and what is happening is that the reaction is going back. That means that with tertiary amines, we cannot have Michael additions. Okay? Next example. What happens if we add an oxygen nucleophile? For example, methanol. Well, the reaction here didn't work. Why? Because methanol is not enough nucleophile to attack here. What we need to do is to do it in basic media. Basically, what we need to do is to use the anion. For example, sodium methoxide. How it's working, we have here, we generate sodium methoxide in methanol. And when we have this anion, okay, it is coming from here. What is happening is that a molecule of methanol is reacting, and what we get is the Michael addition, and we regenerate the methoxide for a new catalytic cycle. I mean, we need catalytic of methanol. Okay? But we need to have a methoxide at the beginning. If we don't have methoxides at the beginning, the reaction will not work. But the mechanism is totally analogous at what we did before. Third example will be with sulfur. Okay, I do the same reaction. We have and I add a thiol. What will happen? Well, we know from the first lesson that thiols are very, very nucleophile. Sulfurs are very nucleophile. Why? Because are less electronegative than the oxygen, and they have a bigger orbitals. Okay, because it's a third period, that means that his orbitals are huge. That means that will be better nucleophiles. Please check the first lesson about it. And a pair of electrons of the sulfur will attack here. We form the same intermediate as usual. And as we did before in the case of the nitrogen, what we do is we remove one of the hydrogens of the sulfur, and then we add one hydrogen in order to protonate the anion. And we generate the Michael additive. Remember that if you want, you can do it only in one step. It's up to you. This negative can take the hydrogen. But I suggest to do it in 2 steps. It's easier. Okay? It's more methodic. If you choose a methodology, do it always. And when you are an expert or you have a lot of experience, then you can do it all in 1 step. Okay? Do we need any catalysis here? No. The sulfur is enough nucleophile to do all the reaction by himself. Okay? And that's all about the mechanism. Remember that this type of compounds, these Michael acceptors, this is called a Michael acceptor because you can do a Michael reaction, okay, are very important in anti-cancer treatments, okay, because basically they can stop the mitosis of the cells. They are stopping the replication of the DNA. And that's all. I hope that you understood the basic mechanisms of the aldol and Michael addition, and see you soon.